Welcome to Lecture 25, whose big idea is an extension of a principle we saw earlier, way back in Lecture 11, the principle of conservation of energy, now into the realm of thermodynamics as well as mechanics. And we're going to be talking about things we can do to ideal gases to change their internal energy or affect other changes in them. And we understand the ideal gas is this very simple system, and that's why we're going to work with it. But the ideas I'm introducing here will apply to any system. So we want to begin looking at the conservation of energy as we understood it back in Lecture 11. In Lecture 11, we were talking about the conservation of mechanical energy, kinetic energy of bulk moving objects, potential energy when we lift something against gravity, and we found that when only conservative forces act, forces that give back the energy we put into them, store it as potential energy, and allow us to get that energy back, then the sum of the kinetic and potential energy didn't change. Conservation of mechanical energy. We explicitly excluded processes like, for example, friction, which involve non-conservative forces, like when I push this book across the table, the book doesn't come running back at me because that's a non-conservative force. And we couldn't apply the principle of conservation of mechanical energy when non-conservative forces were acting. And we know why. What happened is the friction here generated ultimately what we would have called heat, before we knew what heat really was, in the tabletop. We lost mechanical energy, but we didn't really lose energy altogether. We only lost mechanical energy. It changed into another form. What form did it change into? It changed into the internal energy, itself a form of microscopic energy, of kinetic energy and perhaps potential energy of molecules moving around. So it just changed into another form, and we want to express that. So we're going to generalize the principle of conservation of energy to include internal energy. We're going to give it the symbol U. A little bit of confusion there because in mechanics we used U for potential energy. Now we're using it for internal energy. It's also called thermal energy. And we're going to allow non-conservative forces. So we're going to write a statement of conservation of energy that includes the effects of non-conservative forces in generating this internal energy, this random energy of random molecular motion that we used to call heat, and now we know to call internal energy or thermal energy. And we're going to express that in what's called the first law of thermodynamics. And what the first law of thermodynamics talks about is the internal energy of a system, and not so much the internal energy, but changes in internal energy. And it says there are basically two ways to change the internal energy of a system. So the left-hand side of the first law of thermodynamics has the change in the system's internal energy, delta U, change. On the right side is any heat that may have flowed into the system. And again, let me remind you, heat is energy in transit because of a temperature difference. So one way to change a system's internal energy is to add heat. Another way is to do work on the system. By the way, if you've had a course in physics or engineering, you may have seen the first law written with a minus sign on the W. That's commonly done. And that's because the first law was originated in discussions of engines, and engines tend to take in heat and give out work. But I think it's more clear and consistent to write delta U equals Q plus W. And in fact, in my long years of writing textbooks, I've recently made that change in the sign convention. So you will see it written either way, and I'm going to write it with a plus sign on both terms. So if those terms are positive, they mean energy has been added to the system, either as a heat flow or as work being done on the system. Let's look at some examples of how that would work. So over here, I have an obvious situation in which I want to heat some water in a beaker. So what do? I put it on the hot plate. We discussed the hot plate in the context of energy flows. We know that there's a conductive energy flow from the hot plate into the water through the bottom of the beaker, and then there may be convective flows inside there that are heating the water. So that's an obvious way. That's Q. That is changing the internal energy of the water by adding heat. So Q is positive in that case. I'm not doing any work on it. It's just sitting there. On the other hand, I could pick up this spoon and I could shake very vigorously, and I'd have to do it for quite a while. And I probably want to insulate this so I don't lose any energy. But in principle, if I agitated this very violently for a while, doing mechanical work on it, not flowing heat, the spoon is not any hotter than the water. So I'm not causing energy to go from the spoon into the water by a process of heat flow, because heat is energy driven by a temperature difference. I'm simply doing mechanical work. And that mechanical work can also end up as internal energy of the system. So, and in fact, I could do both at the same time. And so what the first law of thermodynamics is telling us is that there are two different ways to change the internal energy of a system. You can add heat and you can do work. And it doesn't matter which you do. The end result is the same. The water gets hotter. That's why we don't call what's in the water heat, because it could have got there by mechanical work, or it could have got there by actually flowing heat. It could have also got in by sticking it in a microwave oven, and that would qualify actually as work, not heat, because that is not random thermal energy that's flowing in that case. So two ways. We can add heat, we can do work, and it doesn't matter which one we do. The end result is the same either way. Now, this idea that work and heat are in some sense equivalent in their ability to change the states of substances, to change their internal energy, goes back a long ways, and it was James Joule in 1845 who really quantified that. And I showed you a picture much earlier of Joule's apparatus and how Joule came to understand thermal energy and heat and work in similar terms, and why the unit of energy, the joule, is named after Joule. But as you can see, it would take a long time and a lot of stirring to heat up that water as easily as I can do it with my hot plate. So it's not trivial to establish this so-called mechanical equivalent of heat. Let's look at how Joule did it. Here's a picture of Joule's apparatus on the left, and I showed you that picture before. It consists of a paddle wheel kind of arrangement that goes into ultimately an insulated can. And on the right, what I didn't show you before, is a diagram of the system. And what happens is strings are wound around that spindle at the top near that crank. The crank is turned slowly to wind up those strings which have weights on them. That puts potential energy into those weights, gravitational potential energy, mechanical energy, and then the weights are let go, they fall, they spin the paddle wheel, and very careful measurements of temperature show how much the internal energy of the water has increased, as measured by the temperature increase. By the way, Joule tried several other methods. He had viscous fluids flowing through tiny holes and generating fluid friction. And he also tried compressed gases, but this experiment was the most successful, and it established the relationship between the measure of energy as thermal energy, which is the calorie, and had been named before people knew that thermal energy was a form of energy, and what's now called the SI system of energy, the SI system's unit of energy, which is the joule. So it established that relationship. So there is Joule's experiment, and what we want to do in the rest of this lecture is look at examples where we do work on systems or we flow heat into them and we understand what happens. And again, the system we're going to use is the ideal gas because, as we saw, the ideal gas is very, very simple. And in particular, the ideal gas is simple because its internal energy and its temperature are directly related because there's no interaction between the molecules. And so they have kinetic energy, and that kinetic energy, that random kinetic energy, is a direct measure of the temperature. We got that wonderful insight about temperature and kinetic energy. So let's look at a particular ideal gas system. And if you study thermodynamics at all, you will see this system over and over and over again ad nauseum because it's a very simple system for understanding what happens in an ideal gas. I have an example of this system over here. It consists of a cylinder, a piston that is free to move up and down in that cylinder. I can therefore change the volume of the gas in the cylinder. I could flow heat into it. I can apply pressure to it. I can make all kinds of changes in the volume, the temperature, and the pressure of that gas. This particular system has some ways to get additional gas in also. And in the ideal situation that I'm going to be discussing, I'm going to imagine, instead of this nice transparent cylinder, I've got a cylinder that is thermally insulated on all the sides, and the piston is also insulated so heat can't flow in and out. But the bottom may or may not be insulated so that we can let heat flow in or out of the system, or we can prevent heat flow as we wish. So that's a kind of physical manifestation of what I'm going to talk about and what I'm showing here in this picture. The ideal gas system, I've got this insulated cylinder, I've got an ideal gas in the cylinder, and it has some volume, some pressure, and some temperature. And I can change those by flowing heat in, by moving the piston and doing work, by letting the piston rise and the gas does work. I can do all kinds of things. And I'm going to describe these things I do, these processes, in what's called a PV diagram, a diagram in which I have volume on the horizontal axis and pressure on the vertical axis. And I imagine starting at some pressure I'll call P sub 1 and some volume V sub 1, and there will be some temperature T sub 1. And given the number n of molecules in there, the ideal gas law, PV equals NKT, would tell me what the temperature is. So any two of those quantities fix the third one. So I'm at some temperature P1, V1, and T1, and maybe there's some final temperature P2, V2, T2. Here the pressure is lower, the volume is bigger. I don't know whether the temperature is higher or lower. I'd have to calculate that. And there might be some process I do, something I do that gradually changes pressure and volume and moves that gas sample to a different place in its PV diagram. And if I do that relatively slowly, the entire gas will stay in equilibrium and it will have a well-defined temperature, and I can think of the gas as going through a sequence of states in that PV diagram. If I do that slowly enough, by the way, there's nothing that would keep me from going back through that same sequence of states, and such a process is called a reversible process. It's a process that occurs slowly enough that you could reverse it, and that plays an important role in more advanced treatments of thermodynamics. Now, I've drawn one path here that I might take in the PV diagram, but I could take another path. I could start out with a nearly constant pressure and then drop it more quickly and end up at the same final point. Or I could take that path. Now, once I'm at one of those points, so the starting point, the final point, any point in between, the state of the gas is completely characterized by its pressure, its volume, and its temperature, regardless of how it got into that state. And yet, what happens in going through those different paths may be quite different, and we want to explore that in more detail. So let's look at the work that gets done by the gas as we play with the piston in one of these piston cylinder systems. And this has really practical applications. Engines are basically devices, gasoline engines, other kinds of engines are devices in which pistons are going up and down in cylinders and work is being done and so on. So this has a lot of practical stuff to do with engines. Also has a lot to do with meteorology, as we'll see at the end of the lecture. So let's look at an example here of work done by a gas. From lecture 11, we know that work is force times distance, and we saw how that led to the situation where if we had a varying force, a force that varied with position, the work was the area under the force position curve. So let's apply that now in our thermodynamic system. So here's our piston. The piston has some area A. There's some pressure of the gas, P, and pressure is force per area. So the gas exerts a force, P times A, on the piston. Let's let the piston rise. Let's let it rise a distance delta x. Well, work is force times distance. So this is the work done by the gas. It's the force the gas is exerting times the distance it's moved. That's PA, the force, times delta x, which I can also write as P times A delta x. But what's A delta x? A delta x is just the volume change. The piston was down here, now it's up here. The gas has expanded into this area or this region, and that's an additional volume, A delta x. And so the gas's volume has changed by an amount delta V. So the work done by the gas in this simple case, and I'm assuming the didn't move very far and so the pressure stayed constant, is P delta V. If the pressure didn't stay constant, then I would look at the area under the PV curve, analogously to the way I looked at the area under the force position curve. And that area, it would be the work done by the gas. It would be the area under the PV curve. Now, that's the work done by the gas. What I put in the first law of thermodynamics was the work done on the gas, and that is the same thing but with a negative sign. So the work done by the work done on the gas is minus P delta V. So that is how we figure out the work done. And I haven't said anything about the particular nature of the process. It could have been any path, and that still would have been true. But for example, a path that went like this, there would have been more work involved because the area would have been bigger. So that's the work done by the gas in any sort of thermodynamic process. Let's take a look now at some specific processes that are actually important in a number of situations, and they're going to be important soon in our understanding of how engines work in particular. So let's look first at one of the simplest kinds of process, a so-called isothermal process. Isothermal means the temperature is the same. So an isothermal process is one that occurs at a constant temperature. How would you make an isothermal process occur? Well, you'd put your gas sample, and again, I'm talking about ideal gases because they're easier to think about. you'd put that ideal gas in contact with what I call a heat reservoir, something that is maintained at a fixed temperature T no matter what happens. It could be something like my hot plate. It could be a huge volume of water, so much water that when you put something else in contact with it, the energy that flows out of it doesn't change the water's temperature significantly. Remember, water has a very high specific heat, so it's hard to change its temperature. You have to flow a lot of energy. So I don't really care how we do it. I'm going to picture it like this, with the heat reservoir imagined to be a great big volume of water or some other substance that just maintains a fixed temperature T. Remember, the bottom of my piston cylinder system might or might not be insulated. If it isn't, I've got these two things in thermal contact, and at least if processes occur slowly enough, the temperature of that gas will always be the temperature of the reservoir. It won't be able to change. So what does the first law say for an isothermal process? The first law always says the change in internal energy is Q plus W. In an ideal gas, the internal energy is proportional to the temperature. That's the beautiful thing about an ideal gas. And since the temperature isn't changing, neither is the internal energy, and therefore delta U is 0 for an isothermal process in an ideal gas. And the first law becomes simply then Q plus W equals 0, or Q equals minus W. What does that mean? It means, for example, if heat flows into this system, so Q is positive, then W will have to be negative, and the system will do work on its surroundings, and it will take that heat energy, and what will happen is the gas, as heat flows into it, will expand, and it will push up on the piston, and it will do work. In other words, negative work will have been done on the gas. On the other hand, if I do work on the gas by, say, pushing down on the piston, so I do positive work on the gas, that says the heat flow into the gas will be negative. In other words, heat will flow out of the gas and into the reservoir. Why is all this happening? Because I'm fixing the temperature. I'm not letting the internal energy of the gas change, because the temperature is fixed and the internal energy is basically a measure of temperature. So that's an isothermal process. We can look at the work done in an isothermal process by taking the ideal gas law. PV is NKT. T is constant, so P then becomes proportional to 1 over V. And so I have a sort of hyperbolic path in the PV diagram. And if you remember from high school math, if you took Algebra 2 or pre-calculus, you don't quite need calculus for this, you defined the natural logarithm function as the area under a hyperbolic curve, a 1 over x curve. And so we have that same kind of curve. And so it's not surprising, without working out the details, that the work done on this gas is something that depends on the amount of gas and the temperature T, and then it depends on the logarithm of the ratio of the initial to final volume. And if you work out whether that logarithm is positive or negative, depending on whether V1 is bigger or smaller than V2, it works either way. You can either go from that upper state P1, V1 to P2, V2, or you can reverse them and go put P1, V1 down at the lower right and go up that curve. And this gives you the work done on the gas. Either way, if that number comes out positive, work is actually done on the gas. If it comes out negative, work is done by the gas. So that's one important process. Another important process is the so-called adiabatic process. In an adiabatic process, there's no heat flow. That's the definition of adiabatic. It means no heat is allowed to flow into or out of the system. You can achieve it by insulating the system from its surroundings, or you can achieve it, so there it is, I put an insulation on the bottom of my piston cylinder system, or you could achieve an adiabatic process by making a process occur very fast, so there's no time for heat to flow out. So you can do it rapidly also. Calculus shows, and I'm not going to prove this, that P times volume to some constant, which is characteristic of a given gas, is a constant in this case. The first law for an adiabatic process, well, the first law reads change in internal energy is Q plus W, but there's no change in internal energy in an adiabatic process, and so Q is 0, and that immediately tells us that delta U is W. If you do work on the system, the internal energy, and therefore the temperature, if it's an ideal gas, goes up. If you look at adiabatic and isothermal processes, there's an interesting distinction, and I'm going to look at the process particularly of expansion. Isothermal, there's no temperature change, no change in internal energy. Adiabatic, there's no heat flow. Work may be done at the expense of internal energy. If a gas expands adiabatically, it does work on its surroundings and its internal energy, and therefore its temperature drop. And so if we look at a picture starting from the same point in the upper left of this diagram, an isothermal process takes us down this hyperbola. An adiabatic process takes us down a steeper curve because the temperature in that case has to drop. Well, let's do a real practical example of this. Let's look at something definitely practical, a diesel engine. A diesel engine is different from a gasoline engine and it has no spark plugs. And the diesel fuel is ignited, or the mixture of fuel and air is actually ignited by the rising temperature associated with a compression that occurs so rapidly that it's essentially adiabatic. There's no time for heat to flow in or out significantly. And a diesel engine might have what's called a compression ratio of about 11:1. That's the ratio of the volume, maximum volume in the cylinder when the piston is at the bottom to the minimum when it's at the top. And this gamma happens to be 1.4 for air, and that has to do with the molecular structure of air as basically diatomic molecules. And the question is, what's the maximum pressure in this cylinder when it's compressed like that? P1, it starts out at 1 atmosphere as we suck air into the engine. The initial volume is V1, whatever that is. There it is. The final volume is V2. That's the compressed volume, and that is V1 divided by 11. We want the pressure P2. We want the pressure here when we're in the minimum state. So here's our equation, which I didn't derive but motivated, for adiabatic expansion or compression. P times V to the gamma, this factor 1.4, is constant. And that's equal to P1 times V1 to the gamma, because that's true anywhere in the process. It's also equal to P2 times V2 to the gamma. But V2, this minimum volume, is V1 divided by 11, because that's the compression ratio. So I'm going to stick that in for V2. I'm going to solve for P2. P2 is P1 V1 divided by V1 over 11 to the gamma, and that's a V1 to the gamma downstairs, and that's a V1 to the gamma upstairs, and they cancel. So it's P1 times 11 to the 1.4 power, and that comes out to be 29 atmospheres. That's a big, high pressure. It takes that kind of high pressure to compress the air in the cylinder enough so it will actually ignite the fuel. That's, by the way, why diesel engines have to be very rugged. They're big, heavy engines, and they're typically used in trucks and buses. They are used in cars, too, and about 50% of cars in Europe are diesels. But diesel engines have to be built more ruggedly than gasoline engines because they have to have this higher compression. You wouldn't want this in a gas engine because the mixture would ignite when you didn't want it to. Let's do a demonstration that shows this process of compression ignition. So over here, I have another piston cylinder system, and you might think that's the cylinder, but that's actually just a safety cylinder. Inside, there's a thinner cylinder of glass, heavy, rugged glass. And at the bottom of it, I've put a small wad of tissue paper. And I'm going to compress that gas adiabatically, and I'm going to ensure that the compression is adiabatic by doing it so fast that there won't be time for heat to flow in and out. I could do it slowly. If I did it very, very slowly, heat would have time to flow in and out of that gas, and I'd have an isothermal process, and the gas would stay at the same temperature. But I'm not going to do it isothermally. I'm going to do it so fast that it is an adiabatic process. So watch carefully at the bottom. There's a little wad of, it's actually just a piece of white tissue paper. Ignition. And you can see the smoke filling the cylinder. Temperature had to go up pretty high to light that little piece of tissue paper. Adiabatic compression occurs when no heat is allowed to flow in or out. In this case, none of the heat or none of the internal energy that developed as a result of the work I did on it when I compressed the cylinder was able to flow out as heat. It simply didn't have enough time before the temperature got high enough to do the ignition. So those are two examples, the diesel engine and this ignition system, that are sort of technological instances. Let's look at a couple now of natural occurrences where we worry about adiabatic compression and expansion in Earth's atmosphere. Normally, it gets cooler as you go up. You climb a mountain, it gets cooler. You fly up in an airplane, and the temperature outside the airplane is very cold. The reason for that is because the atmosphere is basically transparent. Sunlight comes through the atmosphere, heats the surface of the Earth, and then the atmosphere is heated from the surface by conduction and convection and latent heat coming up. So the atmosphere normally cools as you go up, and there's some rate at which it cools. So I've got a graph here that shows temperature on the horizontal axis, altitude on the vertical axis. Temperature is decreasing with altitude. The rate of decrease is called the lapse rate, and it varies with meteorological conditions. So normally that's the situation. Now, imagine some air that gets heated near the surface of the Earth. Maybe you've got a parking lot with its black pavement absorbing a lot of extra sunlight, or maybe you've got a smokestack and heated air is coming out of the smokestack. In any event, that heated air is hotter and therefore less dense than its surroundings, and therefore it's buoyant. It's going to rise. As we saw in Lecture 19, buoyancy forces cause something that's less dense to rise. So it rises. And the question is, what happens after it rises? Well, here is a picture of the rising air. The rising air expands because it's rising into air that is also less dense. And in expanding, it does work, pushing against the pressure of the surrounding air. And if this parcel of air is pretty big and air is a pretty lousy conductor of heat, there isn't much heat flow out through the contact between that rising parcel of warm air and its surroundings, and consequently we can think of that as an adiabatic process. And therefore, no heat is flowing out, therefore very little heat is flowing out, and therefore the gas expands, and it does work against the surrounding air, and so its temperature drops. It cools adiabatically. And there are two possibilities. Does it cool more slowly than the temperature drops in the surrounding air? In that case, it continues to rise, and that's called an unstable atmosphere. That's conditions on a typical, nice, beautiful, clear day. Any parcel of air that starts rising continues to rise upward because it's always warmer than its surroundings. But another possibility is if the temperature rise in the atmosphere is more gradual. Or sometimes a condition called an inversion, it's actually reversed and the atmosphere gets warmer as you go up. But it doesn't have to get warmer. It just has to get cooler at a slower rate than a rising parcel of air would cool. And when that happens, we have a stable atmosphere, and the rising parcel eventually reaches a point where it's in equilibrium with surroundings and it can't rise any farther. And that's what gives rise to dangerous smog conditions. Here's a picture of the two conditions. We see an unstable atmosphere, a clear day. This is the city of Toronto viewed from across the lake. And we see a situation where the atmosphere is stable and the smog is trapped in. The famous smogs of Los Angeles, for instance, are caused by conditions of inversion or conditions where the temperature rise with altitude is slow enough that parcels of rising air eventually reach equilibrium as they cool adiabatically and they're stabilized, and then you can't get rid of the smog and everything else in the atmosphere. There's one example. Here's another example. If you live near the Rocky Mountains, for example, live in a place like Denver, you get these Chinook winds. Chinook is a Native American word that means snow eater. And these Chinook winds occur when cool air high in the mountains falls, it's more dense, and it falls toward the plain, and as it falls downward, it heats up adiabatically. It's now adiabatically compressed. It heats up, and by the time it reaches the ground level, the level of, say, Denver, after coming down from 10,000, 12,000 foot mountains, it is much, much, much warmer. And those are the warm Chinook winds. And if you do the challenge at the end of this lecture, you can do some calculations about the Chinook winds. So there's another meteorological example. Okay, well, let's summarize Lecture 25. We've seen basically a generalization of the principle of conservation of energy called the first law of thermodynamics that talks about the two ways of changing the internal energy of a system by doing work or flowing heat. Thermodynamic processes are described by these paths in the PV diagram. There are many, many thermodynamic processes, but two really important ones are isothermal processes that occur at constant temperature. P times V is a constant in that case, or adiabatic processes that occur in the absence of heat flow, and for them, P times V to some exponent, called the adiabatic exponent, gamma, is a constant. And we've seen several examples of how that works. And if you would like to be done, you're done. But if you would like to get challenged, let's look at a challenge. I'd like you to derive a relationship between pressure and temperature in an adiabatic process. We had a relationship between pressure and volume. Now I'd like you to derive a relationship between temperature and pressure and temperature, and find, first of all, the maximum cylinder temperature in that diesel example, assuming the air started at 20 degrees Celsius, and the temperature on the plane in the Chinook example. Let's assume a temperature of minus 5 Celsius up in the mountains and 60 kilopascal, low pressure up in the high mountains, and a pressure of 90 kilopascal on the plane, and we want to know what the temperature is down on the plane. These problems look very different, but they're basically the same problem. So here's the solution to the challenge problem. First, we're going to solve the ideal gas law for the volume V. The ideal gas law says PV is NKT. We're going to substitute that into the adiabatic relationship PV to the gamma equals constant. We're going to substitute the algebraic solution for V, and we get P to the 1 minus gamma times T to the gamma equals constant. I'm not going to go through the algebra. You'll have done that if you've solved the problem. You're given both P and T at one point, P and T up in the mountains, P and T in the cylinder when it's at its maximum volume, and you're given P at the other point, so all you need to do is solve this relationship for T at the second point and do the numbers. In both cases, we're dealing with air, and air has this adiabatic exponent gamma of 1.4. You do it for the diesel engine, you find a maximum temperature of 765 kelvins. Again, all this needs to be done in absolute temperature. That's about 492 Celsius. You do it for the Chinook winds, and you find the temperature on the plane. Same thing is happening. Adiabatic compression is about 301 kelvins, or 28 degrees Celsius.